Welcome to E-Pathsala. I am Deepa Satish, Assistant Professor in Nutrition. In this module, we are going to see about physical, chemical and microbiological characteristics of dehydrated foods. Before that, let us see what is dehydration or drying. Drying is the oldest method of preserving food. The early American settlers dried foods such as corn, apple slices, currants, grapes and meat. Compared with older methods, drying is quite simple. In fact, you may already have most of the equipment on hand. Dried foods keep well because the moisture content is so low that spoilage organisms cannot grow. Dehydration or drying of foods has long been practiced commercially in the production of spaghetti and other starch products. As a result of advances made during World War II, the technique has been applied to a growing list of food products including fruits, vegetables, skim milk, potatoes, soup mixes and meats. Pathogenic bacteria occasionally withstand the unfavorable environment of dried foods, causing food poisoning when the product is rehydrated and eaten. Control of bacterial contaminants in dried foods requires high quality raw materials having low contamination, adequate sanitation in the processing plant, pasteurization and before drying, and storage conditions that protect from infection by dust, insects and rodents or other animals. Foodstuffs may be dried in air, superheated steam, vacuum or inert gas or by direct application of heat. Air is the most generally used drying medium because it is plentiful and convenient and permits gradual drying, allowing sufficient control to avoid overheating that might result in scorching or discoloration. Air may be used both to transport heat to the food being dried and to carry away liberated moisture vapor. The use of other gases requires special moisture recovery systems. A related technique, freeze drying, employs high vacuum conditions permitting establishment of specific temperature and pressure conditions. The raw food is frozen and the low pressure conditions cause the ice in the food to sublimate directly into a vapor. Adequate control of processing conditions contributes to satisfactory dehydration with substantial retention of nutrient, color, flavor and texture characteristics. Let us see about changes during drying. Drying brings about changes in the final product quality. One of the most obvious changes during drying of cellular as well as non-cellular foods is shrinkage. The type and extent of shrinkage depends upon the rate of drying. For example, on the slow drying of a vegetable dyes, first there is a surface shrinkage. With continued drying, water is removed from the deeper layers and finally from the center, causing continuous shrinkage towards the center with a concave appearance, and the product is dense. With quick high temperature drying of food, the surface becomes dry and rigid long before the center dries out. Thus, when the center dries and shrinks, it pulls away from the rigid surface layer, causing internal splits, voids and honeycomb effects, and the product is less dense. Such a product absorbs water, reconstitutes quicker, more closely resembles the original material and is thus favored by consumers. With foods that contain dissolved sugar and other solutes in high concentration, drying can result in the shrinkage and sealing of the surface pores and cracks. This results in trapping much of the remaining water with the food and drying rate dropping off severely. Dried food pieces may contain voids, cracks and pores of various diameters. The shrinkage and pore clogging by the solutes is known as core hardening. Gradual drying with low surface temperature can minimize core hardening. Some foods which lack structure and are rich in sugar and other materials soften when heated at the elevated temperature of drying. Even after all the water has been removed, the food will be in a thermoplastic tacky condition, giving an impression that they still contain moisture. They stick to the dryer. However, on cooling, thermoplastic solids harden into a crystalline or amorphous glass form. In this more brittle condition, they can be easily removed from the dryer. In addition to the physical changes described above, drying can bring about a range of chemical changes. These contribute to the quality of both the final product and the reconstituted food in terms of color, flavor, texture, viscosity, nutritional value and storage stability. Complete prevention of these changes is virtually impossible. They can be minimized by appropriate technology. Next, we see about effects of food properties on dehydration. The physical factors affecting heat and mass transfer such as temperature, humidity, air velocity, surface area and the like are usually relatively easy to optimize and control and largely determine dryer design. Far more subtle are the properties of food materials that may change during dehydration and affect drying rates and final product quality. In the case of food freezing, it was pointed out that the various food properties affect heat transfer. The picture is more complex with regard to dehydration, since food raw material properties affect both heat and mass transfer, and both can have gross effects on characteristic of dried products. Let us see about constituent orientation. Few foods approach homogeneity at the molecular level. A piece of meat, for example, will have lean or fat interlaced or marbled together. A piece of meat being dried will give up water at different rates in the regions of fat and lean, especially if the water must escape through a fat layer. This suggests that where fat occurs in layers, faster drying will occur if the meat is oriented relative to the source of heat, so that moisture escapes in a line parallel to the layers of fat rather than having to pass through them. The same principle applies to the layers of muscle fibers. The rate of drying will differ depending on whether orientation with respect to the heat source encourage moisture to escape parallel with or transverse to the stratification of muscle fiber. Parallel escape generally gives faster drying. Constituent orientation also applies in food emulsion. If in a food piece or droplet, water is emulsified in oil so that the oil is continuous phase and coats the moisture droplets, then dehydration should be slower than if the emulsion is removed and water is the continuous phase. Sometimes this can be controlled in a manufactured food being dried, but more often we must take what nature gives us. Next we will see about solute concentration. Solutes in solution elevate the boiling point of water systems. This occurs in food dehydration processes. Foods high in sugar or other low molecular weight solutes dry more slowly than foods low in these solubles. What's more, the concentration of solutes becomes greater in the remaining water as drying progresses. This is another factor that slows drying and contributes to the falling rate period in the drying of many foods. Next we will see about binding of water. Water escapes freely from a surface when its vapor pressure is greater than the vapor pressure of the atmosphere above it. Okay. But as a product dies and its free water is progressively removed, the vapor pressure of a unit and the area of the product decreases. This is because there is a less remaining water per unit volume and per unit area, and also because some of the water is held or bound by chemical and physical force to solid constituent of the food. Free water is easiest to remove and evaporated first. Additional water may be loosely held by forces of absorption to food solids. More difficult to remove is water that enters into the colloidal gels, such as when starch, pectin or other gums are present. Still more difficult is the removal of chemically bound water in the form of dehydrates. Example, glucose monohydrate or hydrates, inorganic salts. These phenomena also contributes to the flattening of normal drying curves with the time. Next we will see about what happens to the cellular structure. Solid foods of natural tissues have cellular structure with moisture within the cells. When the tissue is alive, the cell walls and membrane hold moisture within the cells. Such cells have turgor rather than exhibiting leakage or bleeding. When the tissue is blanched or cooked, the cells may still more permeable to moisture. Generally, cooked vegetables, meat or fish will dry more easily than their fresh counterparts, providing cooking does not cause excessive toughening or shrinking. Next we will see about changes on shrinkage, case hardening and thermoplasticity. Even dead cells retain varying degrees of elasticity and will stretch or shrink under stress. If the stress is excessive, then their elastic limit is exceeded and they will not return to their original shape on removal of the stress. One of the most obvious changes during dehydration of cellular as well as non-cellular food is shrinkage. If moisture was removed evenly throughout the mass of perfectly elastic material under turgor, then the material would shrink in an even linear fashion with the removal of moisture. This uniform shrinkage is rarely seen in food materials being dehydrated, since the food pieces generally do not have perfect elasticity and water is not removed evenly throughout the food piece as it is dried. Different food materials exhibit different shrinkage pattern in the course of dehydration. Typical changes of vegetable dyes represented in the following figure. The effect of surface shrinkage is seen in the figure, where the edge and corner gradually pull in, giving a cube or more rounded appearance in the early stages of drying. Continued dehydration gradually removes water from deeper and deeper layers and finally from the center. This causes continued shrinkage toward the center and the concave cube appearance as shown in the figure. Often with quick high temperature drying of food pieces, the surface becomes dry and rigid long before the center has dried out. Then when the center dried and shrinks, it pulls away from the rigid surface layers, causing internal splits, voids and honeycomb effects. Such differences in shrinkage patterns can affect the bulk density of the dried product, that is the weight per unit volume. Products dried rapidly have a rigid, less concave surface and more internal shrinkage and air voids. Products dried slowly are more concave and dense. Both kinds of dried products have advantages and disadvantages. For example, a less dense product will absorb water and reconstituent quicker, is more attractive and more closely resembles the original material, and maybe psychologically more acceptable to the consumer, who frequently interpret greater volume as more substances even though weight is the same. On the other hand, a less dense product is more expensive to package, ship and store, and because of its air voids may be more easily oxidized or otherwise have shortened storage stability. A less dense product often is flavored when it's to be sold directly to the consumers who value appearance and quickly reconstituents of the product, whereas more dense product frequently is preferred by food manufacturers who purchase dehydrated ingredients for further processing and have reconstitution kettles and mixers. Processors are likely to be less concerned with the reconstituents rate than with the container, shipping and storage costs. A special condition related to shrinkage and sealing of the surface of the food piece is known as case hardening. This may occur when there is a very high surface temperature and unbalanced drying of the piece, so that a dry skin forms quickly before most of the internal moisture has had opportunity to migrate to the surface. The rather impermeable skin then traps much of the remaining water within the particle and drying the rate drops off severely. Case hardening is particularly common with foods that contain dissolved sugars and other solutes in high concentration. This can be explained from the various ways water may escape from a product during dehydration. Some of the water move through cell walls and membranes of the cellular foods by molecular diffusion. If the membranes are highly selective against solutes, the water will leave dissolved substances behind. Also, water may be heated to water vapor within a food piece and escape as a water vapor molecule free of solute. But food pieces and food purees being dried also contain voids, cracks and pores of various diameters down to minute capillary size. Water in foods rises in these pores and capillaries, many of which lead to the food surface. Capillary water carries sugars, salts and other materials in solution to the surface of food pieces during dehydration. Then at the surface, the water is evaporated and the solutes are deposited. This is what causes a sticky, sugary extrude on the surface of some fruits in the early stages of drying. This can seal off the surface pores and cracks, which also are shrinking during drying. The combined effects of shrinking and pore clogging from solutes contributes to case hardening. Where case hardening is a problem, it generally can be minimized by lower surface temperatures to promote a more gradual drying throughout the food piece. Many foods are thermoplastic, that is, they soften on heating. A cellular food such as plant and animal tissue has structure and some rigidity even at drying temperature. A fruit or vegetable juice on the other hand lacks structure and it's high in sugars and other materials that are often melt at the drying temperature. Thus, if orange juice or a sugar syrup is dried on a pan or on a heated belt, even after all of the water has been removed, the solids will be the thermoplastic tacky condition, giving the impression that they still contain moisture. They also stick to the pan or belt and be difficult to remove. However, on cooling, the thermoplastic solids harden into crystalline or amorphous glass form. Most belt type dryers are equipped with a cooling belt just prior to scraper knife to facilitate removal of this type of material from the dryer. Next we see on porosity. Many drying technique or treatments given food before drying are aimed at making the structure more porous so as to facilitate mass transfer and thereby speed drying rate. But in some instances, even though potential mass transfer rates are increased by puffing, otherwise opening the structure, the drying rate is not increased. Porous sponge-like structures are excellent insulating bodies and will slow down the rate of heat transfer into the food. The net result depends upon the whether the change is porosity has a great effect on the rate of mass transfer or heat transfer in the particularly food material and drying system. Porosity may be developed by creating steam pressure within the product during drying. The escaping steam tends to puff such a product, as in the case of the potato puff which is shown in the figure. Porosity can be developed also by whipping, foaming a food liquid or puree prior to drying. A stable foam that resides collapse during drying is then desired. Porosity can be developed in a vacuum dryer by rapid escape of water vapor into the high vacuum and by still other means. A great range of chemical changes can take place during food dehydration along with the physical changes already described, and these contribute to the final quality of both the dried items and their reconstituted counterparts in terms of food color, flavor, texture, viscosity, reconstitution rate, and nutritional value and storage stability. These changes frequently are product specific, but a few major types occur in virtually all foods undergoing dehydration. The extent of these changes depends upon the composition of the food and the severity of the drying method. Browning reactions may be caused by enzymatic oxidations of polyphenols and other susceptible compounds if the oxidizing enzymes are not inactivated. Drying temperature, because of the water evaporation cooling effect, often are not insufficient to inactivate these enzymes during drying. So it is common to pasteurize or blanch foods with heat or chemical prior to drying. Caramelization of sugars and scorching of other materials if heat is excessive, another common type of browning. Highly important in food dehydration are non-enzymatic or Maillard browning products from the reaction of aldehyde and amino group of sugars and proteins. Maillard type of browning, like other chemical reactions, is favored by high temperature and by high concentration of the reactive groups in the presence of some water. In the course of dehydration, reactive groups are concentrated. Maillard browning generally proceeds most rapidly during drying when the moisture content is decreased to the range of about 20 to 15%. As moisture content drops further, the rate of Maillard browning slows, so that in dried products below 2% moisture, further color changes from this kind of the browning is minimally perceptible even on long range storage. Drying systems or heating schedule generally are designed to dehydrate rapidly through the 20 to 15% moisture range so as to minimize time of Maillard browning at this optimum condition. Another common consequence of dehydrated food is some loss of ease of rehydration. Some of this is caused by physical shrinkage and distortion of cells and capillaries, but much also results from chemical or physiochemical changes at the colloidal level. Heat and salt concentration affects the water removal, can partially denature proteins which cannot then fully reabsorb and bind water. Starches and gums also may be altered and becomes less hydrophilic. Sugars and salts escape from damaged cells into the water used to reconstitute dehydrated food, resulting in loss of target. These and other chemical changes make reabsorption of water by dried products somewhat less than equal to the original water content and contribute to altered texture. Still, another common chemical changes associated with dehydration is some loss of volatile flavor constituents. This invariably occurs at least to a slight degree. Complete prevention of the flavor loss has, as it proven, virtually impossible, and so methods of trapping and conditioning the evolved vapors from the dryer and adding them back to the dried products are sometimes employed. From other sources, as well as methods of minimizing flavor loss by incorporating gums and other materials into certain liquid foods prior to drying. Some of these materials have flavor fixative properties, others work by coating dried particles and providing a physical barrier against loss of volatile substances. Let us see the conclusion. Dehydration is generally done either for preserving the perishable raw commodity against deterioration or to reduce the cost of packaging, handling, storing and transporting. The most serious constraint for shelf life enhancement is the activity of microorganism. Water in food is reduced to a very low level during dehydration, thus achieving better microbiological preservation and retarding many undesirable reactions during storage owing to the reduction in water activity. Major quality parameters associated with dried food products are the color, visual appeal, shape of product, flavor, microbial load, retention of nutrients, porosity, bulk density, texture, dehydration properties, water activity and chemical stability, preservatives and freedom from pests, insects and other contaminants, as well as freedom from taints and off odors. These parameters need to comply with the specifications of customers and regulations of different importing countries and often can adversely affect the acceptability of dried products. Therefore, quality of dried products depends on many factors such as raw materials, processing environment, packaging, microbial stability, use of additives and temperature of storage.